Let's wrap up this problem-solving section with two more examples. Let's take a look at example 5. We've got a standard piece of paper, and I looked this up online. A standard piece of paper is approximately 0.1 millimeters thick. If you fold the paper in half 10 times, how thick or how tall will the stack be? Or if you were to fold it 20 times, or 30 times, or 40 times, or 50 times, if you were to continually fold that piece of paper, again, that's 0.1 millimeters thick, how tall will that stack be? Think about it, fill out the chart for 1 through 10, and then turn the video back on and check your results. So let's think about if we fold a piece of paper. If I fold it once, and right here I have an XY chart where the X value is the number of folds and the Y value is the thickness in millimeters. So on the first fold, the paper would be 0.2 millimeters thick because when I fold it over, I'd have a 0.1 side and a 0.1 edge together. So 0.1 plus 0.1 is 0.2. When I fold it again, it'll be 4 thicknesses. So it would be 0.4. When I fold it again, it would be 8 thicknesses, 0.8, adding up all those 0.1s. And as you'll probably notice that this number just doubles every time, because every time you fold it, you double the number of edges that have come together. So if you go 1 through 10, by the 10th fold, you should be at 102.4 millimeters. Now we can continue this. We can do it for 11 folds, 12 folds, 15, 20, 30, 40. Here's the problem. To go from the 10th fold to the 15th fold, you would have to figure out 11, 12, 13, and 14 to double 14 to get to 15. Now we could do this if we had enough time and enough pencil grips to get through it. To go from 20 to 30, I would have to figure out 21, 22, 23, all the way through to 29, so I could double the 29th one to get to 30. That takes a lot of time. So what I have next to our numbers, and I have it in orange, is a possible formula. So what I notice is anytime something doubles, it's a continual doubling, it's exponential, and it's like 2 to a power. So when I did my first fold, it was a 0.1 times 2, because I doubled it, which was 0.2. That's the same thing as 0.1 times 2 to the first power. When I folded that, doubled the 0.2 and got 0.4, that's the same thing as a 0.1 times 2 to the second power, because 2 to the second power is 4. Doubling that would be 0.1 times 2 to the third. 2 to the third is 8, and 8 times 0.1 would be 0.8. So we can see a formula developing here that would keep us from having to go through every iteration to get to the next one. Well, we could just jump out a sequence using this formula. And in general terms, we could say this formula is 0.1 times 2 to the nth power. And the nth power is just whatever number of folds you're on. So notice to get on the 10th fold, I would multiply 0.1 times 2 to the 10th. Why don't you use that formula to finish filling out the rest of the table for 15 folds, 20 folds, 30, 40, and 50 folds. So if we use the formula to calculate how thick it is on the 15th fold, it would be 0.1 times 2 to the 15th, 20th fold, 0.1 times 2 to the 20th, 30th fold, and so on. The numbers start to get big really fast. We get 3276.8 millimeters for 15 folds, all the way up to 50 folds, which is 1.25 e to the 14 millimeters. Remember, this is scientific notation. E to the 14 means you would take the point between 1.125 and move it 14 places to the right. It's a pretty large number, but these are all in millimeters. We want the answer in meters, inches, feet, miles. Let's do some conversions. So let me just write down here quickly how you could do some conversions. All right, so let's look at some conversions. First, I made a mistake. I don't want to bother finding the thickness in inches. I only want to work with feet and miles. So I've got 3,276.8 millimeters, and I want to change it to meters. So here is what I know. Using my dimensional analysis, I know that in 1 centimeter, I've got 10 millimeters. That will allow me to cancel my millimeters and get it in centimeters. And I also know that in 1 meter, there's 100 centimeters. That will allow me to cancel out centimeters, and I'm left with my answer in meters. Okay, so if I look at my units, I get all my units to cancel except meters. And in essence, the way this sets up is I end up dividing 3276.8 by 1,000, and that will give me my value in meters. So 3,276.8 millimeters is the same thing as 3.2768 meters. So we could take every one of these answers, divide it by 1,000, and that's going to give us meters. So do that. Okay, I just realized I had made a mistake earlier. I had e to the 12th right here, but when I went back and checked it, that should have been e to the 11. E11. So if you see any time I make a mistake, just send me an email and I'll make sure I'll tell the class about any mistake I may have made in the video. Okay, so if we take all these results in millimeters and divide them all by 1,000, that'll give us our answer in meters. So you can see the list here. For 15 folds, it's 3.2768 meters. For 20 folds, it's 104.857 meters. 30 folds, 107,374 meters. For 40 folds, it's 10,995,162 meters. And for 50 folds, it's 1.125 E11 meters. Now let's change those to feet. I know that there's 3.28 feet in 1 meter, so I could multiply all of those by 3.28 to get me how many feet. And once I know how many feet, I can divide that with 5,280 to give me the number of miles, because in 1 mile there's 5,280 feet. So work on that. Let's look at the results. You might have been working this problem and trying to say and figuring out, oh my God, these numbers are too big. I must have done something wrong. No, you didn't. Okay, at 15 folds, we end up with 10.74 feet. So calculating feet first, 10.74 feet. At 20 folds, we're at 343.9 feet. So if you folded that paper 20 times, it would be 343.9 feet tall. It's crazy, but it's true. If I folded that page 30 times, just kept folding it, got up to 30, it would end up being 66 miles. If I folded it 40 times, it would be 68,000 miles. It's actually 68,302.9 miles. And if I folded it 50 times, it would be 69,942,066 miles. That's an exponential function. Things grow very large, very fast. There's nothing wrong with these numbers. In theory, if you could fold that page 50 times, the thickness would be 69 plus, basically 70 million miles. Where does that get you? It gets you big time in outer space. So that's the power of an exponential function. So no, you didn't do anything wrong. To me, that's amazing. Okay, last example. Cheddar cheese comes in 2-pound bags and mozzarella cheese comes in 5-pound bags. Using entire bags, you want to make a 47-pound mixture of cheese. So you're going to add some 2-pound cheddar cheese bags, some 5-pound mozzarella bags, add them up, put them in, and get 47 pounds. The question is, how many of each type of cheese should you use? And there's more than one solution. Let's work on finding all the possible solutions. Let me give you a hint as far as a strategy or a tool you might want to use. I would set up a table and write down the mozzarellas and cheddars and how many bags of each and see if it would work, if it wouldn't work. So think about using a table. All right, so here's a table I set up. I set up a column for the bags of mozzarella cheese. They're 5 pounds a bag. I set up a column for bags of cheddar cheese. They're 2 pounds a bag. I set up a column just for the number of pounds I would get, and my goal, I was looking for 47 pounds. If I could mix those to make 47, then I found a solution. So I started with 1 bag of mozzarella, which was 5 pounds. Then I subtracted that 5 pounds from the total I was looking for. I subtracted 5 from 47. That means I had 42 pounds left of my mixture. And the question to myself was, could I get enough cheddar cheese bags to make up for those 42 pounds? And since cheddar cheese comes in 2-pound bags, if I divided 42 by 2, that gave me 21, so I could mix 21 bags of cheddar cheese and 1 bag of mozzarella and get a total of 47 pounds. That's a solution. Then I just went down the list to make sure I would get every possible combination, so I jumped to 2 bags of mozzarella, and since they're 5 pounds each, I would have a total of 10 pounds in that mixture. I subtracted 10 from the total amount that I wanted. I wanted 47 pounds. If I took 10 away for the mozzarella, I was left with 37 pounds to compensate for the cheddar cheese. Well, the problem is 37 is not divisible by 2, and I have to use the whole bags. So I couldn't make this mixture using 2 bags of mozzarella because I end up, and you probably noticed, an odd number. And with that odd number, since it's not divisible by 2, which again is the number of pounds in a cheddar cheese bag, that would be no solution. Okay, so I just kind of continued on. I said, all right, let's try 3 bags of mozzarella. That would be 15 pounds because they're 5 pounds apiece. If I take those 15 pounds from 47, that means I have 32 pounds left to try and make up with cheddar cheese. Since cheddar cheese is 2-pound bags and 2 divides into 32 evenly, it gives me 16. I would need 16 bags of cheddar cheese. So 3 bags of mozzarella, 16 bags of cheddar cheese, that would give me 47 pounds, and yes, that's a solution. So continuing in this fashion, go to 4 bags, 5 bags, 6, 7, 8, 9. You'll find a total of 5 solutions to this problem. 3 bags of mozzarella, 16 bags of cheddar cheese, as I said a second ago. Then 5 bags of mozzarella and 11 bags of cheddar cheese. That's another solution. 7 mozzarella, 6 cheddar cheese. That's a solution. 9 mozzarella, 1 cheddar cheese, 47 pounds. That one is a solution. You're going to have one very similar to this in my math lab, and it deals with cars passing over like a wire or something in the road that marks how many vehicles pass on that road at that particular time. So when you're working that one, think about what I did here. A table will help you find every possible solution to that problem. All right, I wish you well.